We humans manage to foul up our precious water supply in countless ways. Fortunately, a few among us are determined to find better answers to this serious and growing problem. Like Tyler Radnicki, an assistant professor of environmental engineering. His entire career, in fact, has been about cleaning up dirty water, and that's a pretty tall order.
Overall, our water supply in this country, it is deteriorating, the quality of that water. It's getting worse over time. I can't tell you if we're in crisis mode or not, but it's definitely going in the negative direction. Aquifers are being used up or they're being contaminated. It's becoming a bigger impact on the water that we do have.
That's not a lot. Only 2.5% of the water on Earth is fresh. 2/3 of that is locked in glaciers and snowfields, leaving a paltry 1.2% that's easily accessible. And much of that is severely contaminated and undrinkable. So what can be done? Well, stick around and we'll explore some unusual clean water technologies that'll give you some reasons to be optimistic. From the College of Engineering at Oregon State University, this is Engineering Out Loud. Dirty water comes in two flavors, stormwater runoff and wastewater. There's a big difference, but both pose serious health and environmental risks.
Wastewater is what people would think of as far as water going down the sink and the toilet of your house. Stormwater, on the other hand, is when it rains, especially in cities and other areas with impervious materials, the water will hit the concrete, the roof, and it'll pick up contaminants, and then it'll flow over land, either into a wastewater treatment plant or it goes straight into a river and then eventually out to sea. This is an area that people have largely been ignoring as far as its impact on water quality.
We could go on and on about all the problems, but I think you get the picture. We're here to talk about solutions, and Tyler has no shortage of ideas.
Yeah, so my research interests and goals revolve around sustainable wastewater and stormwater treatment technologies. In particular, I'm interested in biological systems, so systems that are using bacteria and plants to clean up both the wastewater and the stormwater treatment systems. So we can design improved treatment systems that are more reliable, that can do things faster using less energy.
In previous research, Tyler focused on water purification technologies based on titanium dioxide nanoparticles, and for that, he teamed up with two Oregon companies. One is Puralytics, which makes the Solar Bag water purification system. Fill the 3-liter plastic bag with tainted water, set it under an open sky, and a few hours later, the water is safe to drink. It's big with campers and backpackers, and it can be used to ensure that communities in developing nations have a reliable supply of clean water. The other company is Focal Technologies, a startup that makes the Ray system, an 8-foot diameter lens that magnifies sunlight 200-fold and beams it into heavily polluted water.
Oh yeah, it's a big magnifying glass. It'll light a 2x4 on fire.
The key to both systems is that the dirty water comes into contact with titanium dioxide nanoparticles. By the way, these nanoparticles are really small, like 1/10 to 100th the size of a bacteria, and thousands of bacteria can fit on the period at the end of this sentence. The magic happens when you add sunlight.
When UV light from the sun hits the titanium dioxide nanoparticles, it causes a reaction that creates something called a reactive oxygen species. Essentially, you create these little molecular cannonballs, and they just attack contaminants and turn them into things such as CO2 that's inert that'll go into the atmosphere.
Tyler's work led to performance improvements for both companies' products. More recently, he's been working on a pair of biologically based technologies. To get a solid idea of how each one functions, it helps to look behind the scenes of a run-of-the-mill wastewater treatment plant. Most of us don't give them a second thought. We're just happy they're there, taking care of, business. When effluent from sinks, bathtubs, and toilets enters the plant, it sits around in holding tanks to let the solids settle out. What's left are dissolved contaminants, and one of the big ones is ammonia. Ammonia contains lots of nitrogen, and nitrogen is a very potent fertilizer. If too much reaches rivers, lakes, and streams, it leads to a disastrous outcome called eutrophication.
Which is when you essentially fertilize a lake or a stream, and that can cause big ecological damages That's not good for the environment, but it's also not good for human consumption of that water later on.
If you've ever seen a stream choked with algae and devoid of animals, you've seen eutrophication. So, one of the most important jobs of a treatment plant is removing nitrogen. To do that, the first step is to bubble air, lots of air, up through the water column in those holding tanks. That aeration allows bacteria to convert the nitrogen-rich ammonia into nitrate. But bubbling air takes a lot of energy.
It takes about 60% of the energy at a wastewater treatment plant is dedicated just to bubbling air through water. You convert it to nitrate, and then at that point, you shut off the bubblers. So now you need a different type of bacteria called denitrifying bacteria that require an organic carbon source to take that nitrate and reduce it to N2 gas, which is essentially air.
The carbon source is usually tanks of methanol, which can easily cost more than $1 million a year for even a modest-sized treatment plant.
And so that's the traditional way to remove nitrogen from wastewater.
But Tyler's investigating an approach that's definitely not traditional. It's a twist on an existing technology called Anammox.
Anaerobic ammonia oxidation.
Anammox enlists bacteria that combines the ammonia and nitrite in wastewater to form harmless nitrogen in gas form, and it greatly reduces the need for aeration and completely eliminates expensive methanol from the equation. The cost savings can be huge.
The amount of oxygen, amount of air you have to bubble through the system is reduced by about 60%. So the wastewater treatment plants are very excited at this. They see instant cost savings if they can implement this system into their wastewater treatment plant.
But Anammox requires highly trained personnel to monitor and control the process. That's usually not an issue at big plants located in big cities, but smaller communities are constrained by tighter budgets.
It puts it out of reach for most modest-sized treatment facilities and small-sized treatment facilities, and that's where we wanted to try to take the technology.
Tyler sees a possible solution. Incorporate Anammox into constructed wetlands and let the chemistry kick in and run on cruise control.
It would take this advanced technology that many of the larger cities in the country are actively pursuing to implement and put it into the hands of smaller communities, even the size of Corvallis or smaller, that could take advantage of this technology to produce cleaner wastewater effluent, but to do it more cheaply and put it into something that's relatively simple, relatively passive, such as a wetland, and still get the same type of performance. And that's where the challenge is, taking a very complicated technology and putting it into a simpler system.
Simple, maybe, but not easy. There's this thing called microbial invasion when other bacteria naturally found in the wastewater try to take over.
How do you keep your Anammox bacteria there and working without being outcompeted by these other microorganisms, especially in a system where you don't have a lot of levers to control the temperature and the flow rates? It's very a passive system. How can you sustain that Anammox treatment technology in an environment that's constantly being attacked, so to speak, by other microbes?
That's what he plans to find out. His work is mostly at the lab scale right now, and things look promising. He's also working with Clean Water Services, a water resources management utility in Hillsboro, Oregon, which has built some pilot-scale wetlands, about the size of a horse trough, that receive a small stream of real wastewater. If things work out and a full-size wetland is built, it'll look much like you'd probably imagine a wetland.
To me, it would look kind of like a park where you would have natural plants growing out of the system. The Anammox itself will be buried underground, but there'll be a vertical flow wetland, which will essentially be wastewater trickling over rocks. We'd be treating it, and then it would come out the other end, more than likely into a pond of some sort before eventually reaching off into a river or a creek.
On a very different technology track is FOG, F-O-G, codigestion.
FOG is fats, oils, and greases. So it's what's coming out of your restaurant fryer grease.
To appreciate the ingenuity of FOG, we need to zoom in on a prominent component of most wastewater treatment plants, the anaerobic digester.
You take these organic solids and you put them into a sealed reactor, essentially, so no oxygen, no air. Inside of there, a special group of microorganisms called anaerobic bacteria will start to break down that organic matter. And it takes about 30 days.
One of the byproducts of the process is methane gas. To prevent the release of this potent greenhouse gas into the atmosphere, most plants flare it off.
And really that's a wasted opportunity, because you could take that same gas, that same methane, and burn it and create electricity. But the economics doesn't make sense to buy a generator to burn the methane if you're not producing enough. And most anaerobic digesters don't produce enough to do that.
Adding fog, a major source of carbon, changes the entire equation and amplifies tremendously methane production. So much so that it becomes a valuable commodity. The wastewater treatment plant in Gresham, Oregon, has become energy self-sufficient and now produces more electricity than it consumes. In fact, they sell some back to Pacific Gas and Electric, and they added a second generator to handle the excess methane. When he learned about Gresham's fog co-digestion system, Tyler called them up to get a tour, and then he asked how they determined how much fog to add.
And they just said, well, we just picked them out, and then we called it good. Like, it worked. It made more gas. We're happy with that. And that's where they left it.
So they were kind of guessing.
They were completely guessing, but they were taking it on the safe side. I'm sure they were pretty nervous the first day they put in even that amount, but it seemed to work. And the reason is because they didn't dare risk upsetting the digester.
Because that can spell disaster. If the microbial community inside the digester goes too far out of balance, the system will crash. The digester will go offline, and the sludge, which never stops coming, would have to be trucked to other treatment plants at tremendous cost.
But I can make small versions of these, and I can kill them off all the time and see what happens. And we definitely found differences between the food sources, although we still are working on trying to figure out exactly why this food source behaves in one way and another one behaves in another way.
Tyler has a couple of things in mind. One is to gain a fundamental understanding of how the various fog recipes, so to speak, affect the digester's microbial community. The second objective of his research is to get a better handle on microbial resource management. It's clear that currently the fog process is inexact. Engineers pick a fog source, feed it to the digester, and back off at the first sign of declining performance. But that's letting the microbes dictate the terms.
Microbial resource management, though, flips that on its head a little bit. It's saying that if we understand the microbial dynamics in that system well enough, we can use engineering parameters such as temperature, loading rates, things where you can twist knobs and control flows. We can take those engineering tools and use them to shape the microbial community to perform higher, to make more gas, to recover quicker. You mold the community. You shape it into a structure that will perform better.
And there's no shortage of fog sources. Food producers up and down the Willamette Valley are clamoring to just give away their fog for free to avoid disposal costs. But that variety is one of the greatest challenges to managing the process.
Fog is not a uniform substance. It can be have many different compositions depending on what kind of food products it's coming from. And we're very curious on how does that affect the digesters themselves. Just the composition of the fog is pretty much unknown.
And methane is just the low-hanging fruit. Other byproducts of fog include bioplastics and hydrogen.
There's many possibilities if you can control these very complex microbial communities. We're just now, in the last 2 years or so, starting in that direction.
I asked Tyler how he feels about the future of our clean water predicament when he's feeling at his most optimistic and when he's not so sanguine. On the one hand, he believes that more and more communities will come to view stormwater runoff and wastewater as not just something that needs to be disappeared, but as valuable sources of energy, nutrients, and heavy metal recovery.
And I think this flips the entire paradigm on its head from this is a net cost. We have to treat this to protect our water to this is a net opportunity of here are free resources coming at us if we're smart enough to know how to use them and capture them.
And to tell the truth, he doesn't get into pessimism too much. But he remembers very well someone who did.
I'll never forget when I was an undergraduate, my advisor was very much a pessimist, and every day he'd come in, Dr. Spigarelli, and he'd come in and he goes, "So you depressed yet? Are you depressed yet?" Right? And so this was in the 90s, and things weren't looking very good, and I'm like, no, technology, we can do it. And I just always kind of had this undying, sometimes naive belief that between technology and the human spirit, we'll figure this out. It's not too late, and that's still what drives me today. It's not too late. We can still figure this out. Some things have gotten better, and some things have gotten worse, but there's always reason for hope. If you don't have the hope, then we might as well just stop.
This episode was produced and hosted by me, Steve Franzel, with additional audio editing by Molly Ayton. Thanks, Molly.
You're welcome.
Our intro music is The Ether Bunny by Eyes Closed Audio on SoundCloud and used with permission of a Creative Commons Attribution license. Other music and effects in this episode were also used with appropriate licenses. You can find the links on our website. For more episodes, visit engineeringoutloud.oregonstate.edu or subscribe by searching Engineering Out Loud on your favorite podcast app. Bye now. To get a solid idea of how each Tyler, why can't I say his name?